Hello, everyone. Thank you so much for joining us today. Today, this is the session 42 from Material Science and Engineering Club for scientific discussion. We are gathering here to talk about a specific subject, having critical thinking and discuss more details about a specific topic that we have a main presenter. Today we have, and we are honored to have Mr. Majed Amini, who is the PhD candidate at the University of British Columbia in Canada. So for the beginning, I invite Mr. Amini to introduce himself shortly and tell us about her experience and his experience and his background. And Mr. Amini, if it is able for you, please go ahead, and we are ready to listen to you. Please, after your introduction, start your presentation and give us every 5 minutes a pause to let all participants come and share their idea, their questions. And after that, we can continue at the end of the session. Please go ahead. I think your microphone is mute. Mr. Amini, I think your microphone is mute, and if is it possible, you can start.
Dr. Tabai, do you hear me?
Yes, I can hear you.
Okay. Thanks for the meeting today. And I don't know if Mr. Amini can hear us or not. It seems that he is out now. Maybe he needed to restart.
Yes, possibly he needs to restart his computer, or maybe the Zoom software. Maybe he joined to these meetings in another method with another equipment. Ms. Amini, could you hear us?
Hello.
Hello, Mr. Amini. Thank you for joining us.
Can you hear me?
Yes, we can hear you. If is it possible for you, we can start the meeting right now. This is the session 42. Please introduce yourself and start.
I'm so sorry, I can't hear you. There is no voice.
But I could hear Mr. Amini. I could hear. But not now anymore. If you are talking, Mr. Amini, we cannot
Okay,
hear
I
you.
will start, but if someone asks me any question, please use chat because I can't hear anyone.
Sure, please go ahead.
Can you please make me co-host?
I think there is a problem with your software.
I can't share my screen.
Okay, I will make you host. Okay, right there you can.
Perfect, thank you.
Please go ahead, and from now we can start the meeting. And if it is possible, make it the presentation bigger.
Can you see my screen now?
Yes, we can see.
Okay, perfect. I'm so sorry, everyone. I can't hear anybody, but I will just open the chat. So I will start my presentation. And if you have any question, please use this chat. I don't know what's the problem, but there is no voice for me. So hello again. Thank you so much for your time and for joining this meeting. My name is Majed Amini. I'm a PhD candidate in material science at the University of British Columbia. My supervisor is Dr. Erjman, and I was in Iran for my bachelor and master, and I almost studied chemical engineering and polymer engineering. Also, I worked 3 years in the biggest tire factory in Iran, Bares Tire Company, and I just joined UBC by January 2021. And my project is focusing on conductive 3D printed biocomposite aerogels. Perfect. Today we are going to talk about 3D printing of biocomposites, especially conductive biocomposites. So first of all, we need to define what is bio-based materials. As you know, bio-based materials refer to products that mainly consist of a substance derived from living matter, for example, biomass, or it may refer to products made by processes that use biomass. As you can see here in this slide, the global market size for bio-based materials is increasing day by day, and it's almost like $14 billion by 2018, and it will reach to it will increase by 10% by 2026. So this is a huge number, and it is really important to pay attention to this type of materials. Bio-based polymers are sustainable, and they have powerful potential to modify their surfaces, so they are non-toxic and there is no health concern. Also, if we are going to use a bio-based polymer, we are gonna like less plastic leader, and also they are more marketable and they are strong and lighter. So it's not full screen, sorry. I
No,
just
it's not.
share it, and I'm in the slide mode, Shao.
It's not full screen.
Is that okay now?
Yes.
Perfect. Yes. Okay, perfect. Yeah. So this is so important to pay attention to this type of polymer, and yeah. Perfect. One of the main polymer for bio-based polymers is cellulose, and as you know, cellulose is the most abundant natural polymer. We can have cellulose from wood, plant, or bacteria. And for example, in this slide, we can see how we can extract cellulose from wood. In the first step, we can have microfibrils, and then by doing some chemical or mechanical treatments, we can have nanofibril cellulose. Cellulose consists of beta 1 to 4 D-glucoside units, and it can be repeated more than 10,000 times. Also, if we do a strong hydrolysis, strong acid hydrolysis, we can have a cellulose nanocrystals. So generally, we have two types of nanomaterials by cellulose. One of them is cellulose nanocrystal, and the second one is cellulose nanofiber. And today we are gonna focus on these two types of materials. Cellulose nanocrystal or nanofibril is so important for researchers because they have several applications. For example, due to their favorable properties, hydrophilicity, low cost, biodegradability, and biocompatibility, and also non-toxicity, we can use these type of materials for drug delivery, tissue engineering, bioimaging, wearable sensors, and wound dressing. But before using these materials in these applications, we need to engineer their interaction forces. For example, we have different interaction forces between cellulose particles or fibers, such as double-layered hydrophobic interactions, bridging, and van der Waals or edge bonds. We need to increase, also we need to engineer these type of interactions to have actually better performances in the final applications. How we can do this important job? We can use like, actually we can increase the concentration of the CNC, or CNC is like cellulose nanocrystals, or CNF is cellulose nanofiber. We can increase the concentration of these type of materials. Whenever we increase the concentration, we are gonna like form of a lipotropic liquid crystalline gels, and we can have a strong gel. And later I will explain why we are going to increase the viscosity of these type of materials and why this one is so important for 3D printing, especially inkjet printing or extrusion 3D printing. Also, we can use some polymers like gel thickening polymers, and also we can reduce electrostatic repulsion by ionic liquid. But the most important and actually easiest and straightforward one is using salt. By using salt, we can reduce the debye length, and also we can increase the viscosity of cellulose inks. So here we can see different structure and methods to fabricate this biocomposite. For example, we can have homogeneous composite, segregated composite, preformed composite, layered or porous composite. And we can use different methods to process these polymers. For example, solution, melt blending, coating, freeze drying, filtration, or sol gel template. But what is missing here? Yeah, exactly. 3D printing and 3D structure biocomposite. So 3D printing is one of the best methods to form this biocomposite. And recently it attracted like researcher attention, and we need to focus on this category. So by having 3D printing, we can increase the speed time to market. Also, we can reduce development cost. This method is so easy, I mean, easily accessible. It can produce less waste. Also, we can have creative design by this method. We can have like unlimited shape and geometry, and also we can improve the quality of product by this method. But as you know, we have different type of printing, such as FDM or fused deposition modeling, inkjet printing, electron beam melting, or SLS. Today, I'm going to focus on inkjet printing, especially extrusion printing. And as you can see in this slide, we have different actually shapes with high quality from my recent work, which is based on conductive cellulose. And as you can see in this slide, we have a UBC logo or one chemical structure here. It's P dot, my conductive part. And as you can see, if we connect this small LED, we can see it's conductive or not. So before I'm starting like and before I start talking about my recent work and how we can optimize the quality of printing for biocomposites, especially cellulose biocomposites, if you have any question, please go ahead. If not, we can continue. Yeah, thank you, Sam.
Thank
The
you so
bad
much.
things
So much.
here is that I can't hear anyone, so I would be appreciated if you use chat. I'm so sorry about that. I don't know what's the problem.
Thank you so much, Mr. Amini. If anyone can hear me, please go ahead. Please ask your questions, or if you have other ideas or you want to share your opinion, your experience, please go ahead. We are welcome to hear you. And we are ready to have a discussions. It would be better to don't have just one main presenter. If you want, just open your microphone or raise your hand. You can open microphone and continue. If not, we can continue with Mr. Amini for the rest of his presentation. Okay, so let's go.
Could you go ahead, please?
Okay, thank you. For talking about 3D printed biocomposite, we need to define some novelty, gap, and challenges in this field. Here, I just divided these novelties into 3 categories. Before we are talking about fabricating a 3D, actually conductive ink. So first of all, we need to consider nanoscale. By synthesizing some different conductive particles or polymers with different morphology, we can investigate the effect of nanoscale on the final properties of our materials. Also, since we are going to use some different methods to dry our hydrogel and make it maybe for example aerogels, or using ambient drying or critical drying, we can have different morphology, different structures actually in terms of micros. So aside from nanoscale, microscale is so important for us, and we need to engineer these 2 parts. Also, as you know, we can have, as I told you, we can have complex geometry by using 3D printing, and this complex geometries is, we can call it macro scale. As you can see here in this slide, in the right one, we can print different grid with different size, different mesh, and also different structures. So for my application, since it's a conductive polymer, and I'm gonna use these printed samples for example, for energy storage or for electromagnetic interference shielding, different structure give me a different properties and performances at the final step. So these 3 categories are so important, and we need to consider all of them. In terms of macro scale, which is actually related to this meeting, we need to optimize the 3D printing conditions in the first time. And for one of actually my first works, I tried to optimize the cellulose 3D printing conditions. As you can see here, if we have just cellulose, and if we tilt the vial, it can easily flow. And when our ink just flow, it's not a good candidate for extrusion 3D printing. And I'll tell you why. Because we need actually a high viscous materials. Just for example, imagine we use 3, 5, and 7 weight percentage of cellulose, and whenever we tilt our vial, all samples float. And this, as I told you, these samples are not good for us. So we used the actually different concentration of salt, because as I mentioned, adding salt is one of the straightforward methods to make gel and actually prepare our sample for 3D printing. By using this small amount of salt, we can decrease the debye length, and we can increase the viscosity of our gel. And as we can see here in this slide, whenever we tilt the vial, there is no flow. So this can be a good sign for before start printing. And here we can see the process for my printing. We have extrusion 3D printing, and I used the the pressure that I applied was around 40 to 70 psi, and the speed was 6 to 15 millimeter per second. Also, in the left side of the slide, we can see different structure of 3D printed cellulose nanofibril. And for example, from A, we can see freestanding 3D printed CNF. This is because of adding salts, especially iron-based salts. And here we can, in the C, we can see 3D printed CNF aerogels. And after this step, we can see the quality of our printing, and we can evaluate the quality of that. And from E and F, we can see conductive 3D printed CNF aerogels. And whenever we connect a small LED, we can see it's, for example, it's conductive or not. But before each step, before starting 3D printing, we need to correlate the rheological properties or rheological measurement with 3D printing. This part is so important because before conducting any 3D printing, we need to know the quality of our printing. I mean, we are gonna have like a high quality 3D printed shapes or not. So how we can do that? By doing 3 rheology tests, we can make sure that our sample, our ink is good or not. First of all, we need to run strain sweep test to make sure that we are in the linear viscoelastic area, and then we need to run flow test because for extrusion 3D printing, we need shear thinning behavior. So we need to make sure that our ink is shear thinning behavior. It means that whenever we increase the shear rate, we need to like decrease the viscosity should be decreased. Also, to make sure that we have a filament formation during printing, and we want to like make sure that we have a desired shape after printing, we need to conduct frequency sweep, and we need to evaluate the loss and storage modulus G prime versus G double prime, and let's see what happened. Actually in my last work, I just correlated rheological properties with the printing quality quantitatively, and I will explain that how we can quantitatively correlate these two important actually concepts. Before starting this part, if you have any question, please go ahead. If not, please let me know and I can like continue. Please let me know, say it. Thank you.
Thank you so much.
Yes, I see someone raise their hand. Please go ahead, but yeah, thank you.
Mr. Amir Hossein, please go ahead. Please ask your question. I will try to write for Mr. Amini because he cannot hear us. Please ask your question because the video is recording. We can have your voice.
Dr. Amini, please go ahead.
I see that Amir Hossein raised his hand. If he can open his microphone. I don't know what is the problem. If Mr. Amini can let's him to be okay.
Sir Amini,
Sorry
please
about that.
go ahead.
Well, let's start with our first test. It's strain sweep, and as I told you, we need to make sure that we are in the linear viscoelastic region. And for my recent work, I just tried to use 10 different salts with actually different properties, ranging from monovalent, divalent, and trivalent salts to like chloride and also sulfide and carbonate salts to make sure that we are actually covering the whole periodic table. Okay, sorry. I can share my screen now. I don't know what is happening. Okay. Can you see my screen now?
Yes.
Okay, perfect. Well, as I told you, we chose these 10 different salts to make sure we are covering the whole periodic table, and we actually considered every parameters to actually investigate. As we can see, just imagine the strain rate be less than 1. We have a linear like amount for G prime. We have a constant amount for G prime and G double prime. So we can consider this region as a linear viscoelastic region. So this is so important because we need to run all rheological tests in the linear viscoelastic region. And from A, B, and C, as I mentioned in my previous slides, we can see how whenever we actually add salt, we can increase the viscoelastic properties, and we can have like strong gel. For example, if we like tilt the vial, there is no flow for that. So this test was conducted just for finding the linear viscoelastic region, and by looking at the results, we can find like the shear strain less than 1 can be a linear viscoelastic region. So we need to conduct our rheological test in this region. Here we can see the result of the flow test, and also from like A, and we can see the frequency sweep test by B and C. As you know, as I told you, actually, we selected different salts, and the first parameter that we are going to talk about it is the effect of cation charge number. Since we have monovalent, divalent, and trivalent salt, we want to see what is the effect of cation charge number and the viscoelastic properties, and consequently, at the final, what is the effect of this cation charge number and 3D printing quality. Sorry, Sayed, in slide 10, what is the process time for fabricating those structures? As I told you, we use like the speed for our 3D printing was like 6 to 15 millimeter per second, and it depends on the layer and dimension of the samples. For example, for my sample, I just printed 75 layer sample, and it takes like, for example, 15 to 20 minutes. It depends on the dimension, structure, and layer. Okay. You're welcome. First, as I told you, first parameter is the cation charge number. And as you can see in this slide, for example, take the green line as an example. It's the sample can include sodium bicarbonate, NaHCO3 salts, and it has like the highest viscoelastic properties and viscosity. So we need to talk about it. We need to find why. First one is cation charge number. By increasing cation charge number, I mean moving from monovalent salts to divalent and trivalent salt, we can increase the viscoelastic properties. But what is the reason for that? The first reason is reducing the Debye length. As you know, whenever we increase the cation charge number, we are going to increase the ionic strength. And when we increase the ionic strength, it's like this. For example, imagine we have two fibril, we have two particles of cellulose, and there is a salt between them, and this salt is act like a bridge. Whenever we increase the actually strength of this bridge, it can like reduce the distance between these particles. I mean the diffusion layer, and whenever we increase this layer, we are gonna like make these two particles closer to each other and form the like network between them, entanglement between these fibrils, and increase the concentration. So this is the reason why cation charge number is so important for us. Next one is bonding type. We have different types of salt with different bonding types. Some of them can like produce or can actually form H bond, more H bond, and some of them can like form ion dipole interaction, dipole-dipole interaction. Take like CaSO4 and NaHCO3 as an example. For example, for sodium bicarbonate, we have Na aside from like HCO3 negative, and this like Na can act as an ion dipole interaction, can form this ion dipole interaction between these Na particles with water or with OH groups of cellulose. So whenever we form this bonding type, this type of actually bonding, we are gonna like again like as a bridge, and we are gonna increase the network. This will increase the viscosity, so we can actually form this network between particles. And also, yeah, here we can see how Na can act as a bridge between these fibers. Finally, as we can see here in this slide, by using different salts, imagine like LiCl as a like first one to last one is sodium bicarbonate, we can see how these salts can affect on the printing quality. So all of these samples had the same shape, I mean, designed shape by Katia, but whenever we printed these samples, we can actually see by this picture here, we have different quality of that. Just like one step back before adding salt, we had like 3, 5, and 7 weight percentage of CNC, cellulose on a crystal. And just have a look at the right picture A, please. Whenever we use, the electrostatic layer you described, it is what we call it. Yeah, exactly, double layer, DLO. It's a theory for DLVO double. Yeah, thank you. So before using, okay, can I continue?
Thank you so much, Mr. Amini. Maybe today we have again problem with the Zoom software. If anybody disconnected, you can rejoin to this meeting by the same link. Just click on the link and you can again back to this presentation. Sorry for this problem.
Dr. Tabai, is it the Zoom link that you opened it from your account, or it is from the World Academy's account?
It's from the World Academy.
But we use this license just on Friday, and it was a continuous 2-3 hours, no problem. We should see what is the problem with the setting you do.
Yes, probably. So we can solve this problem.
Maybe I can define a Zoom or you and just share before. We can join with the same link again. Okay.
Okay. Thank you so much.
Okay, thank you. Thank you. Yeah.
If Mr.
Okay, thank you so much. So please have a look at the right side of slide A. When we actually didn't use salt, we had a drop. There is no formation of filaments, so just a drop one. So by having drop, we cannot actually print a 3D structure. But when imagine or like take 7 weight percentage of cellulose with salt as an example, because the viscoelastic properties, also viscosity or yield stresses is like so high for these samples, we have nozzle clogging. So again, these type of samples are not a good candidate for 3D printing because we cannot form a uniform filament. We need a filament formation, but uniform filament formation for having high quality printing. This is the reason why 5 weight percentage of cellulose plus salt is so important. Actually, so it's the best candidate for our samples. And we just continued our research based on these samples, 5 weight percentage of cellulose plus 25 to 100 millimolar salts. And from left side slide, we can see the schematic of 75 layer structure printed with conductive CNC salt inks. In the B and C picture, we have just like cellulose without any salt or conductive part. In D, we just incorporated the iron based salt. Also, we've just used a freeze dryer to make it dry. And from E, we can see a dried sample, dried 3D printed sample. And F is conductive one, just by adding conductive polymers. So till now, so far, we know how concentration and different bound and also cation charge number can affect on rheological properties and consequently on printing fidelity. But as I told you, we need to correlate these two concepts together quantitatively. How we can now, for example, if our yield stress, if our viscosity, if our, for example, loss modulus or storage modulus is like, for example, 10,000 Pascal or something like that, is it a good candidate for 3D printing or not? How we can know this important actually concept. So before starting to talk about that one, I would like to share this table. We recently published this table in my paper in Biomacromolecular Journal, and we believe that this is actually a great guideline for researcher in this field, for researcher, for someone that wants to like print and work on the cellulose-based materials. Imagine we used different types of salts, almost like all of them, different concentration of cellulose, different concentration of different molarity of salts. And here by this table, we can find when we have like non-printable or drop sample, when we can have low quality printing, and what is the best concentration for salt and cellulose to have a high quality printing. And for example, if we increase the concentration of cellulose when we have nozzle clogging. So this table is so important for researcher in this field. But how we can have this table? Also, and honestly, we run like more than 200 rheological tests, ranging from flow test to frequency test, and we can see the result of that, a part of the actually samples here in these slides. We run all these rheological tests, especially frequency sweep and flow test, to find this table. This table is like a summary and actually a conclusion of this presentation and also this research. We can find it how yield stress and the ratio of G prime over G double prime can tell us the printing quality. Here in the last row, we can see the hydrogel and aerogel average line width. The needle that I used for printing these samples was like 250 micron. And if we have a look at these numbers, whenever our number is closer to this number, 250, it means that we actually print a sample in a high quality one, because like the width of the line is almost the same as the needle diameter. So as you know, as you can see in this table, by increasing the yield stress and G prime versus G double prime, we can have a better quality of printing. But the problem, the challenge here is that we cannot increase the yield stress as much as we want, because as you know, we need to apply a pressure on a system to like dominate the yield stresses, because the applied pressure should be higher than yield stress that we have. So we have like a limitation here, but as much as we can, we need to actually increase the yield stress, but it should be less than the applied pressure, the applied pressure in the system. But for G prime versus G double prime, we found that it should be higher than 7, this ratio. It should be like more than 7 to have like a better quality of printing. And this actually finding these results is so important for researchers in this field. So this is the reason why I told you we need to quantitatively correlate rheological properties with printing fidelity. And finally, for more information, you can refer to my last publication in Biomicromolecule Journal. This is a cover photo of my recent work in this journal. We have all of this data that I actually presented here. And also, you can find more information, more justification for each part. Also, regarding the nanoscale, as I told you, because for conductive biocomposite, 3D printed composite, we need to consider three categories, and for nanoscale you can refer to the right side. I mean the ACS applied electronic.
Hello. Hello, everyone. Sorry for the problem. I don't know what is going on with the Zoom. It doesn't help us. If it's possible, we can continue if you have Dr. Amini. It was a technical issue in Zoom. Maybe we can use the another for the next session. We can use the another method to make a Zoom links for the participant to join. It's the second time that we have this problem. Sorry for that. We hope to solve these technical issues second time. I will okay.
Hello again.
Hello again, Mr. Amini, could you hear us? Oh, maybe he cannot hear us. So let's again.
Sorry,
Can
Mr.
you see my
Amini,
screen?
you hear us? No.
Yes,
Okay,
yes,
thank
we
you.
hear you.
Well, as I told you, I don't know what is happening, but as I told you, you can find more information, more justification regarding this like interactions and this like correlation between rheology and printing with in my recent paper in Biomicromolecules. Also for talking about the nanoscale and the effect of nano structure, morphology, and the final performance of biocomposites, we can refer to my ACS Applied Electronic Materials paper. Finally, I would like to thank my supervisor, Professor Arjman, also my advisor, Professor Rojas and Milani, and members of Nanomaterials and Polymer Composite Labs and PNL at the University of British Columbia. Also, I would like to thank the Silks Okanagan Nation for the use of their unceded territory, the land which the research was conducted. Also, I am special thankful to your community, material science and engineering, to give me this opportunity to talk about my research and my fields. Thank you so much, everyone. And if you have any question, please go ahead, and I will be happy to answer. Thank you.
Thank you so much, Mr. Amini. If you can hear us, we can continue in the voice, but if you cannot, if other participant, they have a question or point, you can mention it, open your microphone and talk. Or if you have a question, please write it on the chat and I can read the question, because we need to record the voice also. Please go ahead, you can raise hand or open your microphone. Yes, I think if I correct, Mr. or Mrs. Dordani.
Oh no, yes, but I didn't. I used to say it. I used to computer, so so my one question. Do you hear me or not?
I think Mr. Amini cannot hear. If you can ask a question.
I can hear, but Mr. Amini cannot hear, Dr. Amini.
No, I think because he doesn't
Okay.
answer, it seems that he cannot hear us.
Okay.
So
Okay.
we can ask.
It was a
the
question
question.
of he showed us a very nice tables after 200 measurements or something like that. But I was wondering if he has plotted, for example, yield stress and versus of the G1 to G2. If you plot that, then we can find some curves.
Oh,
But
great question. Yes, liquid printing. This is my last phase of my PhD thesis, and I just started to run actually some experiment with some actually in liquid printing condition.
Oh, sorry, I think Mr. Amini answered the question from Dr. Javadi. Dr. Javadi asked, do you have any experience with 3D printing in liquid? So Mr. Amini answered. Sorry, Professor Rezai, if you can ask your question or repeat your question. I'm writing your question for Mr. Amini.
My question was that you show a very nice, how do you say, table? Yes, table with different kind of the conditions and several measurements, and you give also a table for yield stress versus G1 to G2 and hydrogel, etc., etc. But if you plot these curves, can you find a good relationship, and how you can find this? How we can use your data to predict the behavior of this material? What are the procedures you do?
Well, it depends. If you mean gel printing in liquid or liquid in liquid, which one you mean? When I say liquid, for example, if you just imagine my slides, whenever you tilt your vial, if it's gonna like flow, we consider it as a liquid. But if it's not flow, it's gel. So we have two different like concepts: gel liquid printing or liquid in liquid printing.
Mm-hmm.
My data can predict gel in liquid printing as well. But for liquid printing, we need to like run this experiment, these rheological experiments again, because it's not for fluid materials. It's not for liquid materials.
Thank you.
It's for gel.
Okay, thank you.
Thank
welcome.
you, Professor Rezai. If Dr. Javadi, I see that your hand is raised. Please go ahead, or if you have another question. I think there is no questions and points. Okay, I received a question from Dr. Javadi. He noted that we have developed recently novel encapsulation techniques, which can be used for 3D printing in liquid.
Oh, that would be perfect. Yeah, for sure. Can I just ask you what is the range of viscosity of your material? Or it's a technique, not it's a material, yeah?
Dr. Javadi, if you can open your microphone.
Actually, this is material and method together. We have developed biopolymer surfactant complexes, and the technique is related to a conservation technique.
Thank you, Dr. Javadi. I will try to transfer your answer to Mr. Amini after the session because he cannot hear you. If another one have a question, please ask. Sorry for these methods of conversation.
Perfect. Yeah, I'm so interested. Let's like discuss it whenever you want, and yeah, I'd be happy.
Great. So
That's perfect. Actually, we just use a special type of surfactant to interfacial assembly of for liquid printing. And we just like submitted one paper regarding this one in advanced functional. It's under review now, but it's a lot of actually things to do in this field. And it's a new field, so interesting. And yeah, I'm really interested. Thank you.
Thank you very much. Again, sorry for these systems. We can, Dr. Javadi and Professor Reza,
Yeah, for sure.
you can communicate with Mr. Amini after the sessions. I will try to share his informations, his links in Telegram, in our group in Telegram. So he is open to communicate with you and collaborate for any other possible project. Thank you so much for joining us. We will try to see you and hear you next week around 9 a.m. in PST time. So thanks a lot for your time and your participation in these meetings. I hope to have a great time and beautiful Sunday. Have a great day. Bye.
Thank you, everybody. Goodbye.
Thank you, everybody. Goodbye.
Okay, thank you so much, everyone. Have a great day. Thanks for joining.
Thank you. Bye.